Hello everybody, welcome to the latest edition of Conceptual Astrophysics videos, a series in which we show how to set up and solve introductory astronomy problems for college students. I'm your host, Dr. Christopher Cirola. Today is less of solving a specific problem and more of a derivation. So this particular video is a little more advanced, but I think it's worth it if you don't mind and you have some patience. So Kepler's third law, or p squared equals a cubed, is one of the fundamental equations in introductory astronomy, especially when talking about the solar system. And it's very useful still to this day for professional astronomers. So even though it's a very simple sort of thing, it's also very useful for us. So how do we get that particular formula? Where does it come from? And what I want to do today is show how to derive it from scratch, more or less. So we do need a little bit of information and a little bit of knowledge of math in order to make this work, but not too much. So, for example, the derivation of the third law of Kepler comes from comparing forces, or specifically using the force of gravity and comparing that to the acceleration created by the gravity. What do I mean? So, the force of gravity between two objects at a distance, so Fg, force of gravity, is equal to this. Capital G, which is a constant number, it's a universal constant as a matter of fact. Capital M is the mass of one object. In this case, I'll make it the mass of the sun. Little m is the mass of a second object, and here we'll make that an object like a planet or a comet or an asteroid. And little r squared is the distance between the centers of those two objects. Okay, so that's the force law, if you will, between two objects. All right. Now, we're going to assume for simplicity that our object will be orbiting in a perfect circle. Turns out that for the results, it won't make any difference. If you want a more involved kind of derivation, that's usually above the level of a class like this, and we're going to let it be. I'll just simply say that you do end up getting the same result, even if you go the long way around. So we're going to take that much of a shortcut because it doesn't change the result. What is this then? This is not the distance to the sun in AU. Sorry for the difference in notation there. This little letter AC stands for something called centripetal acceleration, or center-seeking acceleration. So, acceleration is the change of velocity of an object, how it changes its speed and or changes its direction. So, strangely enough, if you have an object orbiting in a perfect circle at constant speed, it still possesses an acceleration. Why? Because while it's not changing its speed, it is changing its direction. It's always changing where it's going, right? So if I, for example, have an object that, say, is moving in, say, this direction, imagine I have an object here that's moving in this direction. If it goes in a circle, notice the direction is always changing, right? And that counts for acceleration. So even though the speed might not be changing, if you change direction, that counts. That particular kind of a circular motion, the acceleration you get is called centripetal acceleration. Now, I'm going to use this formula, turns out, and the formula here is v squared over r. Little v is the speed, or magnitude of the velocity, if you will, of the object. And again, r is the distance between the objects. So, now, in the case here, we're talking about objects orbiting the sun. We're not worried about what the sun's doing. Now, if you look into this much more carefully, you would also find out that the sun also moves a little bit. It doesn't move much, but it is something that is measurable, and in fact, astronomers do measure that kind of motion of the sun or other stars all the time. But it's not going to play into what we're doing here today, and we're not going to have to worry about that. So we'll just simply say that this r is the distance between the center of the sun and the center of our object, and that's close enough for what we need. Last thing here for a formula is this. This little symbol here is the Greek letter sigma, capital sigma, if you will, and it stands for summation. So add up. Sum up. Sum up what? Sum up all the forces. Now notice this F here does not have a subscript, whereas this one does. This F is just forces in general. So whatever forces are available, that's what you're adding together. And for our purposes, forces are a push or a pull. Okay. Now we'll find out for our case here, there's only one force. There's just the gravity force. There's essentially no, say, air drag or friction in space because it's a vacuum. There's no other forces that really matter. There's not anybody physically pushing or pulling the Earth, say, as it orbits the sun. It's only gravity. So there's only one force to sum up, if you will. It makes it kind of simple. But that is a general statement if you were to do physics for other situations. So just to say that. This is the mass, again, of our object that's doing the moving. That would be, say, the Earth or another planet or comet or something. And this, again, is acceleration. Now, again, this is acceleration in general. I'm leaving off the subscript. In this specific case, we're talking about, it'll be centripetal acceleration. But as a general rule, it looks like this. That's something to mention very quickly, by the way. When we set up equations like this, we often have laws or rules that we follow. The laws or rules that we use are always generalized. They're always for general situations. When you apply them to a specific situation, then you actually put in the actual individual numbers or put in subscripts to identify specific things. But the laws themselves are usually generalized, so we can apply them to many situations, right? All right, let's go ahead and set this up. So what we're going to ask is simply this. Let's imagine we have, say, the sun off in the distance here. And remember, a circle with a dot in it stands for the sun. And let's suppose you have something like a planet or a comet or asteroid like this. And that comet or asteroid is in the process of making circular orbits around the sun. I'm not going to draw the full circle, it's too big, but you get the idea, okay? So that's what we have there. Now the distance then from the sun to our object of interest is the letter r, like that. And the speed or velocity of our object at an individual time is something like this. So notice that the speed is perpendicular or at a right angle to this, like that. Now, as this moves in a circle, like I was sort of gesturing before, it's going to go like this. And notice that at any particular point, the distance from the sun to the object will be like this, and the velocity will be like that, always at right angles to each other. Now, that's if it's a perfect circle. That's our assumption. And especially for planets, that turns out to be a good starting point anyway. Okay, so that's a picture that helps maybe solidify what's happening. Okay, so let's ask, what are the forces acting on our little planet? Okay, I'll call it planet for short. So add up all the forces acting on our planet. Well, the forces is just the force of gravity. And looks like this for a force law. Now, I'm going to leave off the negative sign. You might wonder what happened to it, or why is it there in the first place? All the negative sign stands for is attraction. Gravity is a force that pulls things together. So it's always an attractive force. It doesn't mean necessary direction. So it could be going left, it could be going right, up, down, sideways, whatever. But it's always attraction, right? So if we're talking about, say, the force of gravity between, say, the Earth and you, then the direction is down. In the picture I've drawn at the moment, the force of gravity would be pulling our little planet towards the left, towards the sun. But as the planet moves, then that direction will also change, right? So I'm going to leave off the negative sign, knowing that it stands for attraction, we're good. Okay. Now, that's it. There's no other force that really matters here. Like I said before, it's traveling in vacuum. There's nothing else. There's no ropes or pulleys or wheels or springs or anything else attached to our planet. It's floating free. So that's it. So now, this law here of forces says that if you sum up all the forces, that's equal to the mass of the object multiplied by its acceleration. So we write it like this, okay? Now, one more detail on this, we're going to call that a centripetal acceleration in this case, like I was hinting at before. Why am I doing that? Because we said this object is moving in a circle. And circle motion gives us what we call center-seeking or centripetal acceleration. The acceleration is always pointing towards the center of the circle. Okay, and that also tells us why we can not worry about the negative signs. The forces are pointing, or these two parts are pointing in the same direction. This pull of gravity is taking this planet and trying to pull it to the left in my picture, but at this moment of time, the centripetal acceleration is also pointing towards the center of the circle, to the left. So I don't have to worry about a negative sign in case you're wondering what happened to it. All right, so let's start doing some solving, okay? Now, one of the major skills to have when doing derivations is substitution. To take one thing that you know or have a relationship for and trade it out for another statement or relationship in order to get where you want to go. And that's what I'm going to do here. I'm going to take this centripetal acceleration and replace it with this formula. So G capital M little m over r squared now equals m v squared over r, like that. Okay. So let's pause there for a moment and take a look. Now, if you look carefully, you can see that several things are common. So little m and little m shows up on both sides. which means I could divide both sides by little m, and it cancels. So I can get rid of it. Notice that there's two r squareds in the bottom, or denominator here. There's one r in the bottom here. So I can't get rid of both of them, but I do get rid of one of them. So let's get rid of the squared part there. So I just have one r left. This r goes away completely. And I want to take a moment here and write down what that result is. So gm over r equals v squared, like that. Now, this isn't going to lead us to Kepler's third law yet. I want to take a small diversion here very quickly. If we were to solve this for v, you take the square root of both sides, and you come up with this statement, which says what? It says that for any object orbiting the sun, the speed of the object depends upon its distance from the sun. So, capital G is a constant of nature. M is the mass of the sun. Those numbers don't change. Little r is the distance between the objects, right? And so what that means is that as you get further and further from the sun, the speed goes down, specifically as a square root of the distance. But that makes sense if you think about it, right? The further you are from the sun, the slower you're going, the less the pull of gravity is on you. So that all makes sense, and this is specifically how it works. Again, that's a side comment. It's not our main task. What do we do next? Well, let's take a look at this v here carefully and think about this. So this is a perfect circle, right? Well, what is v in general anyway? V is what we call speed, and is a change of distance. I'm going to write that out in words so we can see it. Change of distance divided by a change of time. In other words, if you want to calculate an average speed, simply find the distance you travel, divide by how much time it took you to get there, get your average speed. And we're assuming because of circular motion, the speed will be the same the whole trip. It won't be changing. Now again, this turns out to be a simplification, but it doesn't matter in the long run. If you do this the long way around, you still come up with the same result. So, but that's what we have here. All right, so, well, what kind of change of distance will we have? Well, a common mistake or thought that you could have at first, we say, well, it's the distances are. But that's not what the planet's doing, right? The planet isn't going from here to the sun. The planet is making a circle around the sun, isn't it? And we all know this distance. This is something you get very early on in life. That's the circumference of a circle. Circumference of a circle, if you remember the formula, is 2 pi times radius, or r. By the way, that's why we're using the r to stand for this distance, as opposed to say d for distance. It's a radial distance. It's a radius of a circle, right? So why not just cut to the chase and call it r? Okay, so 2 pi r. All right, what about the change of time? Well, this is the amount of time it takes to complete the full circle. By definition, we call that the period, specifically the orbital period. How long does it take to make a full orbit? Period in general is an idea that physics people use to talk about how much time it takes to repeat yourself. So if I spin around once, that's my rotational period. If I have, say, an object that swings back and forth like a pendulum, that's a pendulum's period. In here, we're talking about an orbital period. How long does it take to make one complete circle? Now, instead of using, say, little t or capital P, because we've used those for other things, I'll do a physics version of this and call it capital T. Capital T then stands for orbital period, to make that clear. So let's go ahead and write that out in words so it's real obvious what I'm talking about. So capital T, why capital T? Because it's a special kind of time. T for time, right? Okay. Now, one more thing before we substitute. It isn't v that's in this equation, it's v squared. So I don't need this, I need this squared. So v squared equals 2 pi r over t squared, like that. Let's flesh this out a little bit more. 2 squared is 2 times 2 or 4, of course. I can just write pi squared and leave it as that. Then r squared divided by capital T squared, like that. Okay. And this tells you there's a relationship between v and t as well, if you look at it carefully. All right, now let's take this and substitute it here. So we're going to take this equation, bring it over here. So gm over r. Now instead of v squared, I have 4 pi squared r squared divided by capital T squared, like this. Okay, so What we'd like to do is simplify this a little bit further to make this recognizable or put it into a form that's easier to use. So I want to consolidate, if you will, and place things in proper places. So let me do that task next. Now, I want to point out something careful here. Notice that r is over here. There's an r squared over here. At first glance, it might look like you could cancel some r's, but you can't, because this r is in the denominator, the bottom. This r squared is in the numerator, or the top, and on the other side of the equation. So as it works out, they're not going to cancel. Okay. Now, what I'm going to do is I want to take, just for simplicity, I'm going to take this t squared and move it over to the left, and take the gm and the r and move them over to the right. Now, how would I do that? Let's take the entire equation, multiply the entire equation by t squared, and then by r, and divide by g and m, like that. And so what happens? How does this work? So if you look carefully, this t squared will cancel the t squared here, but I'm multiplying the entire equation by this, which means both sides get the t squared. So t squared ends up on the left. Or if you prefer to talk about this way, I'll move the t squared from here to there. Okay? And I'm going to leave that'll be the only thing I want on the left-hand side. What's on the right-hand side? Well, I've done nothing to the 4 pi squared, so let's write them out. So 4 pi squared like that. Okay. How about the g and the m? Okay. Notice I'm doing something similar. The g and the m, if I multiply this side, or divide, this side by gm, it cancels on the left. But then if I divide by gm on the right, it shows up on the bottom. So let's put that on the bottom like this. And sometimes it's put in parentheses like this to sort of emphasize that all of those numbers are just constant numbers. No, by the way, when I say constant number, I mean a number that does not change its value. So 4 is a number, pi is a number. Obviously, they don't change values. G is a constant of nature. It's something that doesn't change. And m is the mass of the sun. Okay, so we're going to leave that alone. Last bit, if I multiply everybody by little r divided by r on the left cancels. R squared multiplied by r on the right gives me r cubed. And so this is our result, the generalized version of Kepler's third law of planetary motion. Now, let's compare this to the astronomy version, which you learned looks like this. Okay? Where's the similarities? How's it different? Notice period squared, distance from sun cubed, distance from sun cubed. Those are still present, right? This is the generalized version. This is a simple version. This version over here is specifically using special units in astronomy, right? Earth years and astronomical units for distance. You have to use those units to make the astronomy version work. This version doesn't. This is a general version. You can use any units you want. Now, typically I will say this, that for astronomers or physicists, we'll use things like, say, meters or centimeters and seconds to talk about distances and times. So you'll often see astronomers do that. In our class, or most common, say, introductory astronomy classes, tend to use the metric system, the standardized units, and so that would be, say, meters and seconds. So I would have a period that's expressed in seconds and a distance that's expressed in meters when all said and done. But you don't have to. That's the point. It's a generalized equation. You do have to make sure all your units are consistent, that they all match and make sense, but you don't have to use any particular unit. As long as you're consistent, you can use anything you like. But over here, you must use the years and the AU. But then the similarities are hopefully obvious. Again, period squared is related to the distance from the sun cubed. Okay. Now, why go to the trouble of getting this version for us here? That will be in a separate video. So, thank you to everybody for your attention. This has been Conceptual Astrophysics Videos. I'm your host, Dr. Christopher Cirola. Clear skies, everybody.